This video is going to go through the definition of continuity, the types of functions that are considered continuous or discontinuous, the types of discontinuities, and a few examples that involve the definition of continuity. The definition of continuity states that a function, f of x, is continuous at a specific value x equals c if the following three things are all true. First of all, f of c has to exist. There actually has to be a point at x equals c in order to be continuous there. We have to ensure that the limit as x approaches c of f of x exists, meaning the function on the left-hand and the right-hand sides are both approaching the value at x equals c. And the last thing is that the limit and the point, the value of the point, need to match up. They need to be the same thing. So an illustration of something that would be considered continuous at x equals c would have a point f of c, it would have a limit, and the limit would match the value of that point. Now, the functions we're going to be working with in this course kind of fall into three separate categories. There is the category where we have functions that are continuous for all real numbers. So these are functions that have a domain from negative infinity to positive infinity, and they are continuous everywhere. So your polynomials, sine and cosine graphs, absolute value graphs, radical functions with odd roots. So we're talking about things like the cube root of x, and also exponential functions. There are going to be a couple of functions that are continuous on restricted domains. So this just means that their domains do not exist from negative infinity to positive infinity, but maybe their domain is just one interval or maybe broken up into two or three intervals. So these include your radical functions with even roots, for example, the square root of x, your logarithmic functions, and your rational functions. Your rational functions will have some vertical asymptotes, but there'll be a limited number of vertical asymptotes, and that's what might split it up into a few different intervals. The last category are functions that are not always going to be continuous. For these functions, you really have to be careful about what the domain is that you're working within in order to know if you're continuous or not. So they involve the graphs of tangent, secant, cosecant, and cotangent. All of those graphs involve an infinite number of vertical asymptotes. And so it's therefore really tough to define this as being continuous on a larger interval. So again, you'd have to pay attention to specifically which interval you're investigating with those. And piecewise might fall into this category. Because piecewise have so many places where the pieces stop and jump to another type of function, we need to be careful about whether or not those limits from each of those functions align. So when it comes to the types of discontinuities, if we are going to be discontinuous, we have two different types of categories: a removable discontinuity and a non-removable discontinuity. A removable discontinuity is going to happen as long as your limit exists, but the limit does not match up with the point. So an example of what this might look like, let's say we have x is equal to c right there. We could have a function that has an existing limit at x equals c. However, the actual value of the function is somewhere else. That would be considered a removable discontinuity. Some people look at that and often refer to this as a hole. So in general, when you see that hole in the function, it's considered to be removable. This also works at this other value. I'm going to call this x equals d over here. X equals d is also considered to be a non-removable discontinuity. Even though f of c technically, or I should say f of d, technically does not exist, your limit still exists. So the fact that there's a domain error that happens at x equals d just means you have a removable discontinuity. For a non-removable discontinuity, your limit will not exist. So again, we're going to talk about x is equal to c. At x equals c, even if I fill this point in down here and I have an f of c, because the limit does not exist as we approach c from both sides. Let's rephrase that. You do have a limit from the left, you do have a limit from the right, but because the limits do not agree on the same y value, the overall limit at as x approaches c does not exist, and that creates a non-removable discontinuity. This is sometimes referred to as a jump discontinuity because of the way that the function jumps from one piece to another piece. This also works if the jump does not actually have a point value at that particular x value, similar to the way the removable discontinuities can also exist. So a couple of questions or examples that use this continuous definition. In here, we're going to take a look at this piecewise and try to determine if this piecewise is continuous or not. If it's not, we're going to figure out which x values we have a discontinuity and label it as a removable or non-removable discontinuity. The first thing we're going to look at is each of the individual pieces and what types of functions they are. This very first piece is an absolute value function, and that would be continuous everywhere. That's in that first category. So we know that it's continuous all on its own. Y equals 0 is a constant function, so that would be continuous everywhere as well. And then I have a cube root, and that also has a domain of all real numbers, and it would also be continuous everywhere. So each one of these pieces presented here are continuous. We don't need to worry about any random domain errors that are not being shown. So now what we're going to do is investigate what happens at the point where all of these different pieces combine. And it looks like they all combine at x equals 1, negative 1. So we'll have to take a look at the left-hand limit, the right-hand limit, and the point itself to make sure that they all match. So in order for this to be continuous, we need to ensure that the limit as x approaches negative 1 from the left is the same as the limit as x approaches negative 1 from the right, which is going to be the same as h of negative 1. As long as these three items all agree, then we would have a continuous function. So let's take a look at the limit as x approaches negative 1 from the left. If x is less than negative 1, we're going to approach from the left using this top portion here. So for this one, I'm just going to plug in negative 1 and take a look at what happens. We have a value of 3. If we're going to approach negative 1 from the right, we're going to be using this bottom piece where x is greater than negative 1. So far, we can see that the left-hand limit and the right-hand limit both approach the same value, so we know that the limit actually exists here. The last thing is to take a look at what happens at specifically negative 1, and when x is equal to negative 1, we have a value of 0. So over here, this is just a value of 0. So since our limit exists, but it's not equal to the value at our point, we have a situation going on here with the removable discontinuity, where our function is approaching the same value of 3, but in this case, our point is actually down here sitting on the x-axis. So we know that we are discontinuous at x equals negative 1. H of x is discontinuous at x equals negative 1. There is a removable discontinuity at x equals negative 1, since the limit as x approaches negative 1 of h of x is not equal to h of negative 1. That would be a full justification or a full statement that uses the definition of continuity with that last statement here, since the limit is not equal to that. That is the third aspect or the third part of our definition of continuity that we're using. And it's stating where the discontinuity is happening, and it's also stating that h of x is a discontinuous function. Our last example is what happens if we have a piecewise and we want it to be continuous and we need to figure out what values are going to make this work. So again, we have to remember our three aspects. Since right here we're talking about x is equal to positive 1 this time, we know that the limit as x approaches 1 from the left must be the same as the limit as x approaches 1 from the right. And it has to be the same as the value of f of 1. I recommend that you pause this right now, try this problem out, and then come back and play it and see if you came up with the right answer. Let's take a look to see how you did. Our final values are that a is equal to 0 and b is equal to 2. In the work, we're going to start with the two limits, evaluating from each side. So we're going to plug in 1 into the limit on the left, or to the function part of the function that's on the left. We're going to plug 1 into the part of the function that's on the right, and we're going to come up with values of 2 plus a and a b. We know that these two limits need to be equal to each other, and they need to be equal to f of 1. So f of 1, according to our function, is going to be a value of 2. So therefore, b must be equal to 2, as well as a plus 2 has to be worth 2 as well.